Good evening everyone, this is Ishan Rao. I am a PhD student from IIT Tirupati and this is 7th session for the deep learning, and today we are going to see the basic operation of PyTorch, and we will develop the simplest version of feed-forward network using PyTorch. Okay, so this session will be mostly code based with respect to it, so we'll go through that. And so before sharing my screen, I'll just let you know that we have seen as of now whatever we have done in the coding session from last in the last six sessions. We mostly hard coded whatever we have seen and derived through the lectures in the theory sessions, right? We hard coded it, and now it's time for us to, since we are obviously not going to remember all those equations and all that, we have to make it simplify, and that's where the PyTorch will come into picture. So let me share the screen once. Okay, so yeah, so today's session will be comprised of few points. I will share this notebook right now. So the first, we're going to talk a little bit about the PyTorch, why it is important for us, what are tensors, how to play with the tensors like initializing, slicing tensors, and how it is different from PyTorch, and there is a GPU support of PyTorch as well. So, and how to use GPU in Google Colab, because everything whatever we are coding right now is in Google Colab. So we will see that, and we will see the speed comparisons with respect to the NumPy, PyTorch and PyTorch on GPU. Then there's another beautiful concept apart from tensors in PyTorch is something called as autodiff or autograd. We will look into it, what is it, what it means like that, and then we will write a basic loop for that. So most of today's session will be comprising on this, because if you once understand little bit of this or understand basic concept of this, then you can start appreciating that the feed forward network with PyTorch tensors. So that is something we are going to look at, because now the code, instead of writing 100 lines of code, it will come down to very 10 to 15 lines of code. So it will become very shorter and shorter. So we will go step by step. So for that we will use something using the PyTorch NN class. We'll look at something called as functional, linear, sequential, and Optim. So this some functionals or some APIs that we're going to look at how to use it and how it is making our code short while writing our any deep learning network. And then we will try to write the same thing within CUDA. Okay, so first part is more important for us, and the part of second two is already written in this notebook, but we will talk about it in the last half an hour of the session. So let me first share the notebook with you. I'm posting that in the chat right now. So now you can access this notebook. Okay, now let's start with PyTorch. What is PyTorch and why we are using it on the all the first place? Now, if you have seen, if you have attended the earlier sessions with in the earlier sessions, what we have trying to do is we created the feed forward network or the with back propagation all as it is, like what we have seen the theory lecture. That means we wrote everything mathematically, all the derivation, all the steps that we have to compute, all the learning algorithms, and the steps to perform finding the gradient or plotting the stuff. So we have wrote hundreds and hundreds of lines of code, right? But in practice, it is a kind of it takes lot of background work, and it takes lot of time to write those stuff. So that's why there's something they have provided us. People have provided us with PyTorch, and there's something called as TensorFlow as well. So these two libraries, PyTorch and TensorFlow, let me write here TensorFlow. So these are the common libraries that we have seen people use for writing a machine learning or a deep learning algorithm. Okay, and we're going so now actual now throughout the course, now from this you will actually start for writing these codes, and from now onwards we are going to write any code in these sessions will be on the PyTorch. Okay, now PyTorch is basically is suitable for beginners. It's not like TensorFlow is also suitable for beginners, but if you know PyTorch, you can easily go towards that using TensorFlow. So many beginners, researchers use PyTorch first, and then they can migrate to TensorFlow. So that is totally fine for this. Okay, so this is the PyTorch documentation. Let me give you this website also in the link box. Yeah. Okay. Yeah, so PyTorch is a very beautiful library where most of the stuff that you're writing right now uh, will be shortened with the respect to the APIs and the functions provided by PyTorch. Okay, and it is very useful because now your code will not you're not going to run only on CPU but also run on GPU. Now, if you have followed the recent trend, the rise of GPUs and or the company called NVIDIA, which is the biggest manufacturer of GPUs, graphic processing units, are in demand. So many companies are buying GPUs more and more because now we will see that why, because one simple reason is GPUs, what they do is they speed up the computation very fast compared to CPU. And when we are building very huge models, deep learning models, where it takes thousands of hours to train, we need GPUs kind of system which can make the computation duration short. Okay, so PyTorch is one of this thing, and they have tutorials, a lot of good tutorials to start off with, and you can find a lot of tutorials in the YouTube as well to learn how to do a PyTorch. What I'm going to do today is mostly I tell you the concept of PyTorch which we will need in the upcoming this for making a feedforward network, or the upcoming sessions for CNN, RNNs and all that. Okay, so we will be dealing with that. So lot of information and tutorials are available here. You can take your time after this, and you can start learning this, because eventually the outcome from this course, yes, you need theory background to understand what is happening, but at the same time you should know how to use it practically as well, both and how to how to make a neural network model, and how to run in a CPU and GPU. Okay, so that's one important thing that you have to keep that in mind. Now, uh, the second part, which is the second thing, which is very important right now for you to understand with respect to PyTorch, is something called as tensors. Now, tensors are nothing but is another way of writing a matrix, but it has some more functionalities which PyTorch has given. So, in the doc section, if I can see, so it is writing it as, let me increase the font. Okay. Yeah. So the what tensor is basically is a multi-dimensional matrix. So it's like when you're talking 1000 to 1000 matrix, or k into n matrix, right? Where the input in number of instances versus number of features for each input, right? So that multi-dimensional matrix contains elements with respect to the weights, bias, and that's the parameters of the thing. That is something we are uh, which help me store in tensor. Now we will see also that some more other stuffs that can be performed under uh, under a basic tensor. So basically, within the context of what we are saying is the differentiation, because you have seen a lot of partial differentiation during the theory class. Now the tensor will allow it inherently to apply to perform differentiation or partial differentiation on these elements, right? So that is one major important factor which make tensor very important. And this tensor that we are talking about, the name is now it's very commonly utilized in the world of machine learning and deep learning, because here PyTorch obviously using tensor, also the TensorFlow, you can see the tensor word is there. So tensor is basically a matrix where you can do a lot of mathematical operation on top of it, and you can assume that they are more sophisticated than the simple matrix that you have seen earlier. Okay, so to run to import a PyTorch. So if you want to use in your own local system, at that point of time, you have to download it. So you can go through this PyTorch documentation and you can see how to download it. But if you don't want to do that much of hassle, you can directly jump into using the Google Colab, where all this PyTorch or TensorFlow has already been installed. Okay, to import PyTorch, you have to write import torch. Okay, and then we are using NumPy because we are going to compare our performance of PyTorch tensor with the NumPy arrays. So that's why you are using, and matplotlib for plotting the functions if you are plotting it. Okay, now to initialize a tensor or to write how to write a tensor, you just write torch, which is taking from PyTorch, and once, and then you have to specify the size of the torch. So let's say that is 3 comma, that is 3 rows 2 columns. So the format will be always first write column, first write rows, and then number of rows and followed by number of columns, like that, right? So 3 is number of rows and 2 is number of column, and we are doing toss.1s. That means each element will be a 1, value will be 1. So if you try to run this, okay, torch has not been because I haven't run this. Okay, so let me run the libraries first. Let me import them. Okay, now it has been imported. Okay, now you can see that. So we have made a tensor of 6 elements with 3 rows, that is, and each row has 2 columns, 2 elements, that is 1, and we are initializing the values with ones. So toss.ones, 1 1 1 1 1. Okay, so that is one way to write. Other ways, other things that we can see here is, so let me write other ways of initialization. So instead of ones, you can initialize zeros as well, and toss.rand with respect to this. So that is, if you are toss 0, that means all the values we have putting in the tensor of 3 comma 2 will be all the zeros, and rand value will give us the random values for the tensors. So if we run this again, so we can see that the first tensor x, the size are same for all the 3 tensors with the same variable name, but here the earlier we have initialized with 1, then it was initialized with 2, 0, and there's an initialization of random initialization. Okay, another thing you have to see here is in the parenthesis there are two brackets are there. Now this one outer bracket composed of telling that there's one particular tensor, and then each tensor, each one square bracket will, the one which I am highlighted right now, correspond to the one row. Okay, so this second line I'm highlighting is the second row and followed by third row. Okay, so that's how a tensor will be automatically look like. Now another way of initializing a tensor, see now we are not going to say anything because you may look like it, take it as a matrix. It's a simple matrix, but it has more of the properties as well, which we're going to see as of now. So let's keep the word tensor as of now. Whatever, when we are going to say matrix, instead of matrix, when we are using a PyTorch, we will be using tensors. So now if you want to create a tensor where you just want to create a space but don't want to initialize something, and so the computer will initialize randomly anything. So for that you have to use toss.empty. So what it will do, it will create a space for 3 rows and 2 columns, but it will not initialize the values in it. Okay, it can keep garbage values. Okay, so that is what toss.empty will do. And if you're trying to print it x, if we do this, now we can see that this values, it's not even rand, because rand value will be mostly when we are putting it will be between 0 to 1, but here you can see that very small values are be there. So if you run it again, the values might be different here as well. Oh no, it's keeping the same, so it keeping some garbage value. So this torch empty, where if you don't want to initialize something, you just use torch.empty. Okay, and now if you want to create another tensor with 0 values, but you don't want to but you want to take the shape of a pre-existing tensor, like in this case x. So what you have to write, torch.0 uh, 0 like, and then you have to write another tensor. So what it will take, it will take a shape of x and it will print it. So let me print it y, and so it will, what it will do is, it will generate a tensor y with zeros keeping the shape same as x. Okay. Okay, cool, nice. So this is another way of initialization there, where if you don't, if you have that, if you know that I have a tensor with particular space and I don't want to create any more, you can just create a new tensor with torch zeros underscore like, and just provide the tensor. It will automatically take the shape of the argument tensor that we have passed, in this case x. Okay, so the same this is a y tensor, the highlighted one in the output, and it will have the same shape as the x. Okay, another few more way to initialize a tensor is, if you have seen in the earlier sessions, we have used something called linspace, or the in the NP array. That means we are creating a array with values equally distributed in a particular range. So in torch also we can write it like that. So we will say that linspace, the value should be between 0 to 1, and uh, the number of steps, or the number of points that you want to have between 0 to 1 will be 5. So it will be equally distributed uh, among the 0 to 1 range. Okay, so once we do this, and if we try to print x, okay, so you got a tensor of 1 cross 5, that is 1 row 5 column, and between 0 to 1 with 5 data points equally distributed. So we have found 0, 0.0, 0.0, 0.25, 0.5, 0.75 and 1. Okay, so that is another way of initializing a tensor. And the last one, to just directly write it out a specific tensor by hand. So what you can do, again like this, you have to take a parenthesis, a square bracket which tells that in this square bracket my tensor is, and now I have to write another square bracket where I have to write the values of a row. So I will write like this. So 1 2 will become my one row, and just a minute, yeah, it is removed. Now if I have to write another row, I will write 3 and 4, and I have to write another row 5 and 6. Okay, so if you can see the highlighted brown square brackets, it is the rows, and the green square bracket is comprise all this row in one tensor. So that this is a format by which you can write it up, okay, manually, if you want to write a tensor. Now if you just try to print it, and this is how you will write. So the way the tensor has been printed, the same way you have to write the tensor also to initialize it. Okay, now now what we have to do, just a minute. I think my connection has been okay. So now we have to write for slicing tensor. Let me change the network. I think this is a slow network here. Okay, now you have to slice a tensor. So it's like same way how you slice a particular array, right? The ways you can slice a particular array is the same way you can slice a tensor as well. Now let me write it down how to do that. Okay, so now if you write x dot size, simply you will just get to know the size of a tensor. So this, in this case, 3 cross 3 comma 2, that is 3 rows 2 columns, right? And if you have to slice it, print x comma 1. So what it will tell, that print all rows values of column 1. Okay, so whatever they in column 1, we will show it. So here if I try to run this, so I will get 2, 4, 6. So what does it mean? If you can see here above, the highlighted one, if I do take all the rows, and in that rows I need only the values consist of column 1. So in this case, the actual x value that we have taken from above, it has 2, 4 and 6. So this is the way the slicing has been done in this case. Now if you want to print in this in some other way, just like if you want to print the 0th row and uh, with all the column values, if you want to do that, so that means print first row with all column values. If you run this, so you get 1 and 2. So if you want to print only 1 and 2 for the first row, for that, this is the way slicing has been done. The same way you have seen in the Python, the same concept will apply here as well. So 1 and 2 will be printed as it is. Okay, now this is one way of slicing tensor. Another way, so suppose if you want to access specific value from the tensor, so we have seen the tensor is like this, 1 2 3 4 5 6. Now if you want to access a specific value, so what you have to write, so y is equal to x square bracket 1 comma 1. Okay, so that's first row, first column, in this case second row and second column, because the rows start from 0. Okay, and the 1 will be second column, so like that. So in this case the value will be 4. Okay, 0 0 1 1. So the 4 will has to be printed if you write x11. And if you just print y, and if you just want to see the what is the print y, okay, let's do print y, then we will see how the output is. Okay, now if you can see that the print y is happening, but it is still creating a tensor. So even though we are accessing only one value 4 from the another tensor, it is still creating by somehow by inbuilt it is creating a tensor for y as well. But if we want only scalar value, to get a scalar value of 4, we just need to write y dot item, and you can get the value of 4 as it is. Okay, so by now what we have seen is, we have seen multiple ways to initialize a tensor. The tensor is the main core component of the data structure that we are going to use in our all processing stuff. So there we have seen multiple ways to initialize, and we have seen how to slice the tensor. For like given a tensor, how to get the data from these rows or columns. Okay, now there's something called a reshaping of tensor. So what do you mean by reshaping? So reshaping is more like a what you have seen np.t, right? So if you do t, so it will transform the rows into columns and columns into rows, kind of like that, or into different shapes. So we will see that how we can do it in tensors. So print x, let's say, to get an overview of what is the actual tensor is. So see, the tensor is here like 3 cross 2 with 2 values in each row, right? And we have 3 rows. Now to convert into different view, we can write x dot y equal to x dot view 2 comma 3. That is, I'm just transposing it from 3 cross 2 to 2 cross 3. Okay, so it will just reshape, the view will reshape the tensor x. Okay, and just if I just print the y, so you can see I just reshape this value as 1 2 3 4 5 6 kind of like 2 rows 3 columns. Instead of 3 rows 2 columns, I just convert to 2 rows and 3 columns like this. So that's one way of reshaping. Another way of reshaping is, suppose you want only one column, no other rows, like that. So I know the number of elements here is 6 here, and I will write -1. So so if I just write like this, and if I do print y, so all the 6 rows I will reshape it, that 3 cross 2 will be converted into 6 cross 1. So now the the output will be 6 cross 1. Okay. Now another way of identifying is, let's suppose you have more than 6 elements and you want to, but you know it's a multiple of 6, but you don't know how many columns it will take. So let's say it has 36, let's suppose X has 36 elements and you know that it's a multiple of 6. So what you say, you just write for each row, my rows will be 6, and the PyTorch has to decide how many number of columns should be like. So for that, what it will do, it will try to it will automatically calculate by dividing the number of elements with number of rows, and it will calculate the number of columns. Okay, so this is another property of view, where if you write -1, the PyTorch will automatically calculate the how many number of columns do I need based on the total number of elements. Okay, now just a minute. Yeah, now we will do some simple TensorFlow operation quickly, and like addition, subtraction, and multiplication, so that we can get an idea how it is happening, and then we will compare the NumPy and PyTorch value. Okay, so if I am initializing, so I will take a new torch, torch.ones, and that is I'm initializing one value and with 3 cross 2 values. Okay, and I'm also doing the same stuff for y as well. So I'm creating another tensor. Just a minute. Yeah, so y is equal to, okay, let me correct this. Yeah, so x and y with 3 cross torch 1 of 3 cross 2. So I have a tensor for that, and I'll just write x plus y. Okay, so if I just do this, so it will do a pointwise operation. So I hope by this time you know what is pointwise operation. That is, it will, so whatever the value of x will at particular position is, the same way it will take the y position as well. Okay, okay, okay. Just one quick thing. Am I able to? Are you able to listen me properly? Because my second device is not connecting. So please let me know if it is. Are you able to hear me properly? Say yes or no in the chat box. I will get to know. Oh, now it's okay. Okay, so sorry if there's some disturbance in my net. I can feel it because my second device is not able to connect properly. Okay. Okay. Uh, okay, so we are doing pointwise operation as of now. We have two tensors. Um, yeah, now we have two tensors x and y with values 1 and 1, and we are doing z equal to x plus y. If we just print z, so you can see it is 2 2 2 2 2. So that means pointwise operation means, so whatever the value at position 0 0 on x and y, it is calculating at that point of only. Okay, so the like the way you have seen the matrix addition, the same way it is happening here. That is a pointwise. Now same way if you want to do for multiplication subtraction, let me copy this. So if I just need to do minus, and here I just need to do multiplication. If I do this, so it makes sense, like I have a tensor with only one value, and if I'm adding 1 plus 1 is becoming 2, so all elements will come 2. 0 for subtraction, it will be 0, 1 minus 1 0, and the multiplication 1 into 1 will be 1, right? So these simple tensor operations. Another way of adding a simple tensor value will be z is equal to y dot add x. So that means I will create a copy here. So okay, so let me print it, then I will just tell you how it is work. Why? Okay, so earlier a y was only 1 1 1 1 1. So when I'm doing y dot x, only the value of z is changing, not the value of y. Okay, so that's why the above one is z, that is 2 2 2 2 2, and the y is 1 1 1 as it is, right? But if you want that you want to update the value of y as well along with the z. So what you can do, you just need to do a small change here. Let me copy paste. Yeah, so if I add this, if I put this underscore and add underscore, so what it will do, it will, okay, let's run it and then I will write it down here as a comment. So what will happening, so along with updating the z, the y is also getting updated simultaneously in the place. So that means that along with z tensor, our y tensor is also getting updated with the operation being performed. So in this case the operation is addition, so whatever the value of z it is you are getting, the same value y also getting as the same y also value is getting updated simultaneously. Okay, now this is a very simple basic operation. Now let's try to understand, or let's try to see that why tensors are being used instead of numpy. Numpys are very good, pretty good, and we have used as of now very most of the time numpys only, but now we will see that the why PyTorch is much faster with respect to NumPy. Okay, so we will do that. So to write, to convert a tensor array into NumPy, so you have to write n underscore np means x, which is a tensor, underscore NumPy, which is a NumPy. So we just write n dot NumPy, x dot NumPy, and yes, that will be means is storing the tensor value in the NumPy array. And I'll just do is print type of x and type of x underscore np, and I'll just print it out, print x underscore np. Okay, so we have what we have done, x underscore np is we have the x called tensor already available. So what we have done, we have created a np numpy array for that with a variable name x underscore np, and we can see the type of that as class x as torch tensor and the x underscore np as numpy nd array, and this is how the numpy array will look like, which is kind of similar to the tensor that we have seen here, but only difference is a tensor will explicitly mention above as like it is a tensor, and numpy array will not tell it like this. Okay, so this is one thing. Another thing, that if you want to convert a numpy array into a tensor, that is also we can do. So just write a equal to np dot random dot rand and randn, and just create 5 random numbers, and we just print the value of that np array. And if you want to do a PyTorch, a underscore ptv means a tensor, a PyTorch variable. So you just need to use torch dot from underscore numpy, and you just pass the value of a. So it will create a tensor with the values of numpy array, and just let's see the type of both the variables a and a underscore pt, and print a underscore pt. So right now what we have written in this code is we are creating a numpy array, we are just printing it. So this is the some random value variable that we have seen here as 1 cross 5. Okay, so the a class is numpy array, and then we have created a underscore pt, which is a tensor. So the tensor of 1 cross 5, the same shape as shape as the numpy array will created as it is, but also it also telling the type of variables, the values I have, that is torch dot float 64. Okay, so that is one way of looking at it. Now another way, so to now let's start looking at the timing of how much for a particular case, how much time computation, how much time a numpy array is taking, and how much time PyTorch tensor is taking. Okay, so for do that, there's a small percentage time is there. So it's a kind of function which will measure a sub function, which if you just write directly like it, so when this cell is going to run, it will calculate the how much time will it take to perform the certain operation written in this cell. Okay, so it's a kind of macro operation we have written here. So let me write one thing. So I will create a, let's say, range of 100, and let me create a NP array. So I'm going to do a simple addition or basic operation with respect to this, and we will see how it is going to run. Np dot random dot random 100 cross 100. Okay, now we just do a basic simple operation a cross b, and we will see how it is going to run. And the same thing we're going to run for the PyTorch as well. So let me write it down here. So instead of a here, so I will just write torch dot random, and little formatting here that I have to keep that into square brackets. Okay, and yeah, so I think, yeah, that's it. So let's see. So we have created, so above code is basically we are going to calculate time how much performance will be taken to add A and B matrices, that is NumPy array, and how much time will be take for tensor, the same operation but with tensor. So let's run it here. Okay, so now we can see that typical for a NumPy array to get added for 100 cross 100 matrices is a maybe taking 83.1 millisecond, but for tensors of the same size it is taking 32 milliseconds, which is quite less than half of what we have seen here. So or maybe 3x time it has a speed of with respect to it, so which is pretty good, right? So let's do another thing. This is still a very small basic operation. Let's do a matrix multiplication and see how much time will it take. So I have to write np dot matmul. I have to pass a and b as a value here, and here in torch I will write c is equal to torch dot matmul a cross b. Okay, so let me run it again. So now again the NumPy array we have, and we are going to, so the time we are calculating is for the all the time, the 100 number of times it is going to run, and each time we are creating an array of 100 cross 100, and each time we are calculating 100 times we are doing the matrix multiplication. So let's see how much time will it take for both NumPy and TensorFlow. So it takes around 260 millisecond, and still for matrix multiplication, which is pretty complex and it takes a lot of time in general settings, it is still doing pretty fast. So that is what the thing that we want to establish here is tensor operations are pretty much faster compared to this, and when you're going to scale it up, where you're going to have millions of parameters and all that, at that point of time tensor will be more useful than using a NumPy array. So that is what we want to establish from here. Let's say maybe let's take a little bit more bigger value with respect to this to establish our claim. So let's take, so here instead of, I will take range of 10, and maybe the matrix will be 10,000 to 10,000. The same setting we are going to do for uh, tensor as well, PyTorch tensor. So here I'll just keep it 10,000. So now the variable matrix addition, simple addition that we are doing is pretty high. The values of matrix are pretty big. So let's see how much time will it take. Okay, as we can see that, okay, so range is pretty big here, that is around 100. For 100 times we are going to add 100 times the a and b will be created, and it will give c equal to a plus b. It will calculate for the matrix addition. So as we can see, there's already more than 30 seconds maybe, and still running, and it's taking a lot of time. And this values that we are seeing 1000 cross 10,000 cross 10,000 is pretty normal as you start making a normal deep neural network. So this is a quite common in nature, and we can see that it's taking a lot of time with respect to it. Okay, so by the time it will do, so let me recap by the time what we have done. So what we have seen when you start using PyTorch, a PyTorch, you have to you will come to know with the concept of something called as tensor, right? So we have seen various way through which we can initialize a tensor. That's the first thing. Okay, so we have seen 3 or 4 ways where we can initialize a value in the tensor, and this is how a tensor, typical tensor, look like. Same like matrix, but with a few modification the how you show it. Okay, then to slice, and you can approach same slicing operation as you can do a slicing operation in NumPy array, so that we have seen here. So with like same colon, comma 1 or 2, where the first values will denote the rows, and the second values denotes the value in the column. Okay, so that is something we have seen with respect to slicing of a tensor. Then we have seen that using view we can reshape our tensors, like the way we can do in the in NumPy we use np.reshape, but in here you have to use the view as it is. And then we have seen the simple tensor operation, that is x plus y, x minus y, x into y, and all that. So this is simple, this is a pointwise operation. That means it's not like matrix multiplication. So whatever the position of a tensor here in x and y, we will take that position and we'll just add or subtract it, okay, or the multiply it. So this is a pointwise operation that we have done. Now after that, what we try to see that how much speed up or difference is there with respect to NumPy and PyTorch with respect to it. So we have created a simple loop. We are doing basic operation like a c equal to a plus b, that's matrix addition or matrix multiplication with respect to both the NumPy array and the tensor. And as of now we have seen that it is taking it takes very less time for tensor operations to compute the same kind of value, and NumPy will take a lot of time. And here also we can see right now that still the operation is not done. I think I should have reduced the range, which I have done them pretty much fast. So let it run it, uh, but it will, as of now we can see clearly for sure that NumPy array take a lot of time for computation, and tensor will help us to reduce that complexity, the computation power, because it has been more optimized in the background. Okay, now we will see the CUDA support. Before that, let me see if there is any question, and then we'll go to the CUDA support. That means how to use a GPU and this Google Colab. That is first thing I will tell you, and then follow that we will see how to run the same operations that we have seen here with the CUDA, and how much speed up we are getting with the help of GPU. Okay. Okay, so the question is, Bapronda, the CPU time in NumPy array is more because of the fact that it uses single core for all its computation, and can it be speed up by parallelization of code in the CPU? The tensor out of box uses parallelization in all commits, so uses all the code in CPU and it's fast. Unfortunately, I can't answer that because I haven't seen the code or why it is actually pretty big with respect why the NumPy is very slow with respect to it. I have to see that how it's actually doing with respect to the background of the code. Um, what you are saying might be now has been implemented by this time of now. What you're saying that it is using only single code, that's not possible. They might have been using multiple cores as well. But the way they are doing might be much more, they might have certain algorithms that which it making fast. So I can't comment as of now that NumPy using only single core and the tensor using multiple cores as of now. um, okay, but if this is the actual this answer, that will be pretty good with respect to, and this will be kind of strange also, that if a tensor can be used as a parallelization of multiple cores in a system, a CPU can have multiple cores, so why the NumPy array cannot be do? So that's a one question that is something it's not clear for me, and maybe I will check it in the docs or maybe some other place, and I can let you know. Okay. uh, Intel one API is there, sir. Okay, so might be yes, it might be doing this. So as of now, I haven't checked it that why NumPy is as particularly slow for the parallelization, but I think it has NumPy for sure have provided something for parallelization for sure, because it has been there for so long. So we, by using that, we might be able to get it much clearer, but I haven't used that as of now, because once you start using tensors, you don't need to go to NumPy array as of now, unless you keep certain data into NumPy array as an input. Okay, I think it is going to take a lot of time with respect to this. Okay, that's fine. Let it take, or maybe what I can do, let me stop it for both the process. I will reduce the range, that will be much better. So let me do with 5 because it's taking a lot of time. Because I have to change the instance as of now. Okay, so to use CUDA, by the time it will run fast now. By the time, so we have to use CUDA support, and PyTorch will support GPU system very fast. The more the better GPU system are, the more faster it will run. Okay, so to check whether your system has CUDA or not, you just write this command tos.cuda.device count, see then how many number of GPUs are there. So check number of GPUs in the system. Okay, so I'll just run it once it's done over. So we can see that for even for 5 range, it is taking only 43 seconds, kind of like that. Now for torch, it is taking 11 seconds. That is about 4x speed up that we have seen with respect to the PyTorch. So we can easily say that PyTorch in a CPU run more faster than the NumPy. Why it is able to do that, don't have a particular answer for that. I need to check that. Maybe by next session I will let you know. And if Pranod is saying correctly, there's an Intel API which is actually helping the PyTorch to run it parallelly on multiple cores. Okay, now to see the whether we have CUDA support here or not, so you have to write this command tos.cuda devices count. Now we have seen that it has a 0 count. Okay, now to since because Google Colab by default give you CPU. Now if you want to use a GPU system here, so what you have to do, you have to go to edit, you have to go to notebook settings. Okay, now the hardware, you have to see the hardware accelerator here. In this case you have chosen CPU. Now you have to use T4 GPU. Okay, and once you do this, you have to terminate the current session. You have to start with the current GPU, because your system will be changing. So I will clicking on OK, and then I will save it. So now what Colab will do, it will assign me another system where there is a GPU support. So it is happening right now here. Now it is connected. Now we can see here it is written here Google Compute Engine backend, that is GPU. So if I run this command again, torch is not defined. Okay, so I need to, since that session was over, earlier session, so let me rerun this again. I will import the libraries. Okay, test is done, and let me run this again. Okay, now the one is there, that means I have one GPU. To know that what kind of GPU I have, I'll just do tos.cuda.device. So this operation will give me the object identifier of the CUDA device, which I'm going to use, and tos.cuda.get device name of the 0th position. Yeah, I think it is correct. So it will give me a GPU name. So there's a GPU called Tesla T4 that we can check it online, what is the configuration of that, but this is what we're going to get. Now once we get this, now the object CUDA, this is a CUDA device, this is the object at particular instance is there. Now what we have to do is we have to create a variable for this so that we can use this. So we can write tos.device, and we have to give the value CUDA at 0, because there's only one device, so we have to write as CUDA 0. If there are more devices, then we have to write the specific device which we want to use. Okay, so this is CUDA 0 equal to toss.device CUDA codes CUDA colon 0. Now once we do this, it is initialized. Now we can use the CUDA right now. So what we have to do is a equal to let me define the ones new tensors here. Now whenever I'm going to use a CUDA, I have to specify the device which I'm going to use. So here I have to specify that the CUDA is 0. So that's the one thing I have to do. Another thing, okay, yeah, let me create another tensor for here. So I'll create the same tensor with B, and I'm going to do C is equal to A plus B. This simple operation that we are doing, and if we run this and print C, so it is telling that okay, this a tensor is there. We have created a tensor with 3 cross 2 with values 1 1 each, and when it's adding, it's giving me 2 2 2, and it has been performed a device CUDA 0. Okay, so the same CUDA 0 that we have defined here. Now once we have done this, once we define the CUDA and all that, now let's try to do the same stuff that we have seen earlier with respect to torch, one running on the CPU and one running on the GPU. Okay, so let me take this code as it is, and now we will see how much speed up we are getting when we are going to use with the typical torch running on CPU and when we are going to run that on a GPU. Okay, so to do that, let's differentiate few stuff here. So let me increase the range so that we can get better understanding of the values of time. So A is equal to range is n, and the range we are giving 10,000 cross 10,000, and here instead of okay, so we are doing this with respect to CPU. Let me write here a CPU. Okay, and what we are doing, if we just want to add this two tensors, so we'll do b underscore CPU dot add a underscore CPU. Okay, and if you add underscore, you will put the value will be stored in B CPU itself. Okay, so this is the first thing we will do, and here in the device, here in the second code, what we're going to do, we are going to specify on which device you have to run. So we are specifying CUDA as 0. So let me write it down here. That means this code will be run on a GPU. We'll do this, and here we will add it as B dot underscore a add underscore a. So we do that here, it will run. Now one more thing we can do is we can also see for the numpy array. So let me take it numpy array here as well. Sorry. Okay, so this is the numpy array, and do I need to add? Maybe mostly in the C plus B, I will just do np dot add b comma a. Okay, fine. So what we'll do, this is a CPU. It will the tensor addition of two tensor will run on CPU. The numpy array will also run on CPU. Only one tensor with GPU we will see, and we will see how it is going to work out. Okay, so let me run this 3 cells. Let's see how much time will it take, because it's a pretty big matrix of 10,000 cross 10,000 cross, and we are doing it for 10 times. This is happening on the CPU, the first one running, the second will run on GPU, and the third one for a numpy array. Now interesting thing is, you can see here for tensor, if it's running on CPU, I'm highlighting the code right now, there it takes almost 18.2 seconds. But if you can see here, GPU, it is running on 17.4 milliseconds, that is approx 1000 speed up, 1000 times it is more running more faster than the one which we have seen in CPU. So that is the more that's the power of using a tensor in a GPU. It will make your computation much more faster, and that's why there is a high demand of GPU as of now, because we can write the code and it will do all this stuff in a very much faster rate. Okay, so same, the numpy array that we have run here, it will run on 30.5 seconds, which is much slower than what we have seen for the GPU of 17.4 milliseconds. So this is the difference between milliseconds and seconds. So with the speaker we have seen a lot of scale up has been happened with respect to the uh, uh, CUDA device. Now same thing, if you're going to run, let me run for a matmul operation only for the GPU. I will just show you for GPU only, such that we can establish that it takes lot of it runs a lot fast even for matrix operation when you're doing in a GPU. So the same configuration, I'll just keep it, maybe let's keep it 5 itself, and we will just do torch dot matmul, and we will do a cross b, and let's run this. It has completed very fastly, that is within the millisecond, that is around 131 milliseconds. Obviously it will matrix multiplication is much more complex than a simple addition of two tensors, but it still has done pretty good. That is still it is there within the limit of a less than 1 second. So that's what we can say that uh, about the TensorFlows. Say PyTorch, that PyTorch has a variable called tensor, and once you use tensor with GPUs, the speed of your completion will be pretty high. Okay, now with that being said, now we have to go to the another property of a tensor, which is called as autodiff or autograd, which is a pretty good property of a tensor, which is provided by PyTorch, and we will see that how we are going to use it and how we are going to utilize the power of autograd to compute our feedforward network. Okay, so since it's only 1 hour, maybe we can take a break of 5 minutes and we will come back with respect to this. One side note, CUDA is very headache. I am totally agreeing with you. Running CUDA, installing CUDA in your system is one of the biggest tasks. For me, last time I installed CUDA, it took me 2-3 days because I have to reinstall it multiple times. But right now, you don't have to worry about that. You just can do use Google Colab as of now. Once you get comfortable with it, you can start using CUDA in your system. Okay, so we'll take 5 minutes break, and then we will start the session one more time again with the autograd functionality. Okay. Okay, welcome back everyone. So we will start from where we are left as of now. So we have seen the basic operation of TensorFlow and all that. Now we will see the main important part of the quality of a tensor and the reason why we are using tensor, which is basically the autograd or autodiff in this case. That means that if you have a typical tensor, then by theory classes as of now you might have seen that you can yeah, to do a partial derivation you have to apply a certain chain rule, right, with respect to this function. Now what you can do, tensor will allow you the ability to perform the same kind of differentiation or finding the grad function, stating if you mention all the function related to that particular tensor. So it will do automatically in the background. You don't have to write everything on their own. Let's see what do I mean by, let's see that, and then we will talk about that. So let's make this first thing. So we are initializing torch.1 once, and that is same as 3 cross 2, and what we are stating that this tensor can perform grad. So we can do grad, requires grad, and we will write it as true. Okay, so that means if I have to write simply, x tensor can be differentiated with other functions. Okay, so this is one thing that we want to say, and let me print it one more time here. So this will be here as x. So now we have a tensor called x now, and we can perform some differentiation with respect to that is we know. So how do we do that? So let's define certain function here. So let's suppose y is equal to x plus 5. This will be 0.5 so pointwise operation, and when you do this, print will become 1 plus 5, that is 666. That is one thing. There's the first operation we are performing, and then we are doing z equal to y into y, that is y square plus 1. And if you do this and then print z, so you're going to perform an z tensor. Now once you do this, let me do the fourth operation here, that is torch.sum z. So if I do this, so I will take all the elements of the tensor and just print the scalar value of that, which will be itself is a tensor, that is 37 into 6 will become 22222. Okay, so 37, I hope you can understand why it is coming, because each element of y is 6, so y square is 36 plus 1 that we are doing, so it's a pointwise operation, so each element will become 37. Now, so from x we have defined three operations, three more functions associated with it, that is x, from x we got y, from y we got z, and z from we got t. Okay, now what if I want to differentiate t with respect to x? That is something we have seen, that what if we want to differentiate loss function with respect to particular weight, right? So for do that, what we have to write a command called t dot backward, because t is also a grad function, and you can see here a certain property here where for each tensor you are writing a grad function, and you are writing something of sum backward and grad function add backward. So what is doing, it's kind of bookkeeping that is doing. Why it is happening? Because it is related to a tensor called x, which where you can do differentiability, right? So that's why, so whatever the functions or the new tensors you are making as of now, it will keep a it will try to keep a bookkeeping of a particular grad function that you are trying to use, right? So it is by default it is doing add backwards and all. This is by default. Sorry, add backwards is used when you are doing customized function. The customized function x plus y is a customized function, y square plus 1 is a customized function, like that. And toss dot sum is a something by default function, so it is doing sum backward. Okay, so when we apply t dot backward, now what you will do, we're going to differentiate t tensor t with respect to x, right? And then if we print it out, x dot grad, that is the value after the differentiation, that is derivative or partial derivative of t with respect to x, we are getting, oh, I haven't run this, sorry. So we're getting some value of 12. Okay, so let's try to understand what this autograd function is doing. Okay, so by default, if simple sentence, autograd or autodiff function is that for a given tensor you can perform differentiation on that automatically. This is something you can't do for a numpy array or any other array, only in tensor you can do that. So this is the major advantage that you're doing, because as you have seen in the theory lecture, whatever the grad or graded descent you're trying to find it out in the learning algorithm, there you're finding the grad, and there you're writing big functions and a lot of steps you have to involve. But here you can do everything very simultaneously in the background. You don't have to do anything, you don't have to write anything. Automatically it will do differentiation in the background. You just need to define the functions. Okay, so let's see from this text that we have seen here. So I'm just highlighting it here. So how you get the 12 value in the each tensor. So what we're saying, when we apply t dot backward, what we're saying, we are tracing back t with respect to the x, where the original tensor where you have applied the gradient function. Okay, so what is doing, t equal to summation of zi, that is t dot sum. This I'm highlighting here, the 15 cell, t equal to t dot sum. So that is something we are seeing here, summation of zi. Okay, now zi is representative as yi square plus 1, that is same here, z equal to y square plus 1. Okay, then yi is equal to, y is defined as xi plus 5. Similarly here y equal to x plus 5. So we are tracing back t to the x. So if you want to find a derivative of t with respect to x, that is a partial derivation, what you have to do, we can write it as which is equivalent to partial derivative of z equivalent to x. Why z equal to x? Because it's a summation of that, so we can directly write it as it is, because t is not, we are not defining t as a function of x, so we can directly write it as partial derivative of z with respect to x. And how we can write it as partial derivative of z with respect to y and partial derivative y with respect to x. So once we do this, we get this value of 2yi into x. How we do that? So if we do differentiation of z, that is y square plus 1 with respect to y, you get 2yi. So this is the value you're getting. And when you do yi, that is yi is equal to x plus I. When you try to differentiate this xi plus y with respect to x, you get the value of 1. Now once you get this, now what you are doing is at x is equal to 1, the y at x equal to 1, y is equal to 6, because of this function, right? So we just substituted this value on this this, and then we got the 12, that is 2 into 6 into 1. Once xi is not there, so we will take assume it as it is, so we'll get the value 1, and that's why you're getting the value of tensor of x grad as 12, for each of the elements. Okay, so what we are seeing here is with respect to is that given a tensor and you just tell that okay, you have to perform some grad function of on that tensor, and you initialize certain function values, that is like y, z and t at that point of time, and you once you do backward, so it will trace out back to the from t to the point of the tensor where you are actually want to perform the grad function, that is grade differentiation here, and then it will pass out the values as uh, pass out the values by computing it automatically by the PyTorch. Okay, to make it more intuitive, let's take another example, one more example, so that we can get it much better clear. Okay, so let's take another example for here, and what I will do is say everything will be similar, only few things I will change. So x will be toss dot ones 3 comma 2. Okay, and it requires gradient. Okay, now why we are telling one particular tensor gradient, why not others, we'll get to know in some time, because once we will map it with the weights and bias as well, so there we'll get it. Now we are creating one new function called r, where we are writing it as 1 plus 1 divided by 1 plus toss dot exp minus y. Okay, and yeah, this is correct, and then you do print r, how the print r will look like, and then you do toss dot sum, that is for r value you sum with all the elements of the tensor, and do you do x dot backwards, that is you're going to do find the derivative of x with respect function s with respect to x value, and then you will do print dot x dot grad. Now, if you have seen this R function, you might be similar, you have seen this earlier as well, which is called as sigmoid function. This is sigmoid, typical sigmoid function that we are writing it here. So what you can assume that x is a kind of weights, and this x weight will be written, the weights will be calculated using y function which is called as x plus y, and you're going to compute that weights with respect to the sigmoid function. Okay, and you're doing a partial derivative of that sigmoid function on the weights, and let's see what the output will be look like. So earlier the value of when we are doing this, x is actually 1 value, that is 3 cross 2 tensor, it has all the 1 values, and then you create a y tensor which is basically 6 value, and then we applied r function on that, which will give you this 0.9975975 like that, and with the grad function of mul backward. This is something, if you're not able to understand, you have to see the docs for that to understand it, but this is a kind of bookkeeping doing. And then what it is doing, it is trying doing a back s dot backward, that means it's trying to find a gradient of s function with respect to x means x here is the gradient, and this is the final x dot dat gradient. Okay, uh, so this is the one way of understanding. So to look at this, you can see that to find x dot x partial derivative of s with respect to partial derivative of x, you have to do partial derivative x with respect to r and partial derivative for r with respect to x. Once you're able to do this, you will get the values of grad function. Okay, so here you can assume x as a weight as well. Okay, so what we have seen here, we are defining certain functions, and x is basically the weight matrix that we have and how fastly and quickly it is actually trying to compute all this thing by default without us writing any equations on top of it. Okay, so this is the beauty of the tensors that we can see. Okay, now once that is done, now let's take like kind of example of autodiff with respect to the what we have seen earlier. So like let's take a simple typical neuron where we have a parameter called w and b, and let's see how we can find the grad value of that. Okay, so if we earlier we have write a lot of line of codes based on the mathematical derivation that we have taken out. Let's see how we can do find the grad function of w and b for updating the weights that we have. That how we used to do, we have to find a grad w, delta w, and triangle w and triangle b, which is basically the grad values of that, and we're going to use that grad value to update the weights. Okay, let's see how we can do that in this case. So we just define a simple random value 20, let's say 20 values, one column, and we are saying that it requires you need to compute the grad of this variable, and y is equal to 3 into x plus 2. We have defined that this is the actual function that we are trying to this is actual true function, and what we're trying to see, we're trying to create an approximate function with respect to it. Okay, so let's do this, and let's create torch tensor for weights and bias. So torch tensor, we're creating only, keeping only one value for weight right now. We will increase it slowly. Let's see first this part. So this part is done, that is we have initialized the weight vector or the weight value, and similarly we do for the b as well. Okay, now my neuron function will be y hat, which I'm trying to approximate, and I'm saying that it will be w dot x plus b. So I have to find the value of w and b in this case, and try to achieve this w and b equivalent to or near to 3 and 2. Okay, so let's see, we will do that. So to do that, we have to apply the loss function, obviously. So loss function will be, we are taking the square loss function here. So t toss dot sum, and we are writing y hat minus y, and we are doing square of it. So this is a simple square law, mean square error, not mean square error, we are just taking square error because we are taking only once time. Okay, so let's run this also. So we initialize the tensor of WB as 1, and we are finding the loss of that also. Let's print the loss, and the loss is 81 point something, which is pretty high with respect to it. We will see that what else we can do with respect to that. And if we do backward, so when we do loss dot backward, that means you're going to find a gradient. So what we are finding gradient, we are trying to find a gradient of w and b with respect to loss function. Okay, so if once we do this loss dot backward, it will run, and if we try to print w dot grad, how it is happening, it is we don't know, it is in the background, PyTorch is taking care of that. So when we do loss dot backward, you're trying to calculate loss function with respect to w and b, just like how we have done in the theory lectures. And if we just print w dot grad and b dot grad, so we have seen that some value is there, it's negative to negative. That means we have to increase the value of tensors as of now. Okay, so this is one thing that we have to take care of mind. So now let's see that how, what we have seen, we have just taken a one case, one instance where we want to approximate the value of x to reach a y equal to 3x plus 2, and we have w and b, and we have run all this process only once now, but we usually use epochs in that, right? So we will combine this all code and we'll try to run the loop. So since we have learning rate as one of the parameters, we'll keep it as it is, and then we will have w and b, where we have only one values, that is one tensor with value 1. Okay, so wb is like this, and we are printing w and b earlier, how it is going to look like, and then we're going to run this 10 times, this for loop, that is considered like as a epoch. 10 times you're going to run, and we're going to initialize x here, that is the input thing, and this is the our actual y value. Okay, and this is the predicted y value, and then we will try to find the loss with respect to it, and we'll do the loss dot backwards. So till now everything, till this point everything is similar than earlier what we have done. Okay, we are initializing x and y, we are trying to find the y hat, approximate the y hat function, we are finding loss function, and from loss function we try to find the gradient of w and b, which is we have defined earlier in the outside the loop. Now what we're doing, similar with the how we update the weights, that is w equal to w minus learning rate into w grad, and b equal to b minus learning rate into b grad. That is something we are trying to do. Okay, now to update the weights in this case, what we are doing, we are doing something called as torch dot no grad. Okay, so what does it means? What is doing is, if you don't write this function as it is, what the PyTorch will assume that this is this WB, whatever we are writing it as, it may be another function. So it will not take a differentiation with respect to it, and it will assign it to some different kind of values. So we don't want that. We want to tell the torch that okay, the loss dot backward, whatever the function has been initialized, you keep it as it is. Don't keep W and B, this highlighted function, into your bookkeeping. Okay, so any code with this under the torch.nograd, it will tells the PyTorch that don't compute anything on that, just use the function as it is. Okay, so we will use this, whatever the W grad and B grad we are getting from the value from the output of loss dot backward, we are substituting here and we are updating the value. Okay, now once we are done with this, we are again initializing reinitializing the grad value with 0. Okay, because the grad will change in every single epoch, and we are going to print the W and updated W and B value over each epoch. So let's try to run this and see what it will happen. So it's a kind of simple sigmoid function we have written without stating anything. With all the differentiation equation, big equation that we have seen, we are just trying to put it into this simple code. Okay, so now let's see what is happening. So first value, first row, first column we can see is basically the weights, and the second column is basically the bias. Now it started with 1 0 1 and 1 for weight and bias, and what you can see that it is in each epoch the value of weight and bias are changing. So this is the highlighted one is epoch 1, then this is epoch 2. Now if you can see here, by the time of 10th epoch it is coming closer to 3 and minus 2. So it is the weight will be 2.998, which is equivalent to 3, and here minus bias is minus 1.98, which is equivalent to minus 2, which is something what we are trying to approximate here, which is y equal to 3x plus 2, right? So this is something, this without stating any neuron, we are trying to compute the whole function as it is into with the help of torch, and the torch look with the function loss dot backward. Okay, so again I'm trying to reiterate it again and again. Tensor has the ability where you can do perform partial differentiation again and again and in a pretty much faster rate. Okay, so that's the beauty of the tensors which you can see. Okay, now let's see for the same thing. So what I'm doing here is the same code as earlier, but here we are going to compute the time, that how much time will it take to compute the whole code. Okay, and another change is, instead of having one weights, I'm going to have a n weights here. Okay, and I'm defining n weights, how many weights I should have, and I'm defining the number of epochs I should have, the learning rate I should have. Okay, so I have to need to learn the weights of n values, and bias will be 1 as it is. Okay, so you can assume like this, that you have you have one single neuron, for that you have a one bias, and you have giving maybe 1 million inputs to that neuron. Okay, so you can assume like that. And the same in the for loop, we are running with for 200 epochs, and we are assigning the x value as random, we are assigning random values to this input x, and this y is equal to is similar to 3x plus 3 into x minus 2, but since the value of n is here is very big, so what we are trying to do, we are trying to create a tensor out of it. We are creating a dot product of that, where we are initializing the 3 into 1 the n values with 1, and we are initializing it 3 into 1 into x. Okay, so 3x and minus 2, we are trying to keep it into y function, and we want to do what we want that y hat should the value of wx should approximate us to give this y function. Okay, we are calculating the loss using the square error loss, and we are doing the loss using loss dot backward. We're trying to do a partial differentiation of loss function with respect to w and b, and similarly we are updating the value of w and b because the w dot grad and b dot grad we are getting from loss function, and we are reinitializing the grad into 0 after each and every epoch. So let's run this thing. So it's a quite big input, and it will take a lot of time with respect to it. Let's see how much time will it take. Now the same thing, the same code that we have written earlier above, we are going to write it down here using CUDA, and we will see how much time will it take for here. The same settings is everything same, only difference here is that we are telling that the device where it should run it should be CUDA, basically a GPU. Okay, and we will see how much time will it take with respect to this. Okay, so it is taking little time, so let's wait for few seconds and few minutes. I will run this GPU one also. Okay, so what this whole code and which I am highlighting is basically a typical sigmoid neuron function with various weights input, various and one bias, and you're doing partial derivative, you're identifying the grad function for W and B, everything, and you written all the stuff in a one single line of one very short line of code, maybe 15-20 lines of code. Okay, now what we will do is after this we will try to build a feed forward network directly using the PyTorch with very few lines of code. Instead of writing hundreds of lines of code and we are writing a lot of derivation and output of derivation of that, we will try to reduce that using one single aspect by removing certain aspect which will be handled automatically by PyTorch. So the same code that we have written in run on CPU would take 40.3 seconds. The same code in the GPU will take 5 seconds. So it is like 8x speed that we can see that in 5 seconds the whole this learning of the sigmoid neuron, let's assume it as a sigmoid neuron, we are able to do that sigmoid neuron, typical one single neuron in 5 seconds in GPU time. Okay, so let me see if we have any questions, and then we will go to the part 2, which is we will run all this stuff. Now we will start the using the see the concept of tensor and the autograd function, that is the differentiation which is PyTorch is automatically calculating the background for making us a simple feed forward neural network. Okay, if you have any doubt. Okay, okay, so I haven't seen any questions, so let's start with this. So this is the second part of it. I'm most of the code, all of the code has been written. I'm going to run it. I'm going to tell you where we are trying to shorten the code with the by the default functions of the PyTorch, which is making our life much easier. So most of the functions that you are seeing here is pretty by this time you might by this time you might have known, so I'm not going to tell this part. So I've already run this import function, so wherever the new function libraries I'm going to import, I will going to tell you at that point of time. So when we do seed function torch.manual.seed, so it is for reproducibility. So whatever I'm trying to run here, it is it is in the hope that when you're going to run the same code in your system or in your Google Colab, the output what you're seeing here should be same. Okay, and this is for matplotlib color, that how I want the output my graph should look like. So for that I've write a customized function for it. Okay, now what we are doing is we are going to generate a data set, the same as earlier that we have seen in last few sessions, the classification thing where we have four classes of data points consist of and total the number of data points are 1000. So each data point is about 250, each color data point is 250 data points, and we have created a test and validation data set using train test split by satisfying the label. Now let's go to the main thing where we're trying from where our PyTorch journey will start. Here what we are doing, after doing the train test split, we are converting this x train, xval, y train, y into a tensor. So how you can do that? Using a map function, you specify that the whatever the input inside will become a tensor. Okay, so x train by x, y train, xval, y train, yval will be converted into this, and these are the now it will become a typical tensor value. Okay, so you can see the torch.size is there. So this torch.size tells that this x train and y train is basically is our tensor value, or became tensor. Okay. Okay, now let's go to see this defined model. So what we are defining model here is, so this model is to tell that how our network will look like. So this will be to look at this. So this will be like, let me write it here. So A1 is the pre-activation function. So let me write A1 or A2 is the pre-activation function, and h1 and h2 are activation function. Let's say h1 is activation function because we have only one layer, one hidden layer. So output layer h2 in this case will be a loss function here, where loss function can be cross entropy for classification and or mean square error. Okay, so what we have done, this model is there where we are trying to calculate that given an input, that is x in this case, x in this case, we are doing a matrix multiplication of this tensor x with weights which we are going to initialize and the bias. So considering the weights here are let's say n, sorry, the input let's say are n cross 2, weights will be 2 cross 2. So how the our value will our network will be look like, I should have taken the image. So the input layer will have two neurons, let's say two neurons kind of thing, that is that means each input has n features, right, like that. Okay, or let's say two instead of two input. Okay, now we have hidden layer, one hidden layer has two neurons. Okay, so that's why we have a 2 cross 2, that is from each input I'm going to have weights for two neurons each. Okay, and my output layer has four neurons. Why four neurons? Because our image, our data is consist of four different classes, that's why we have four neurons with respect to it. Okay, so that is 2 cross 4, that means from each neuron in the hidden layer I'm giving a four inputs, four weights into that. Okay, so a1 is the from input layer to the hidden layer I'm getting a pre-activation function, so I'm doing the w cross x plus bias. Okay, and then I'm applying on that pre-activation function, I'm applying the sigmoid function on top of that. After applying sigmoid function, I'm going to pass the weights to the output layer, which will be considered as a pre-activation function or pre-activation part of the neurons in the output layer, which will be w2, that is weights 2 into h1, because this will become as an input for us, and the bias of the each neuron. Okay, so it will be like n cross 2, which is the matrix multiplication of the h1 and the weights, and the bias is 2 cross 4. Okay, sorry, so h1 is n cross 2 and the weights is 2 cross 4, because that is two neurons with four output values we are getting for the, because the output layer is four neurons, right? So we are getting n cross 4, and then h2. Now here some complex thing is coming, that is a2 dot what we are doing is, here we are trying to do a softmax function, applying a softmax function here. So h2 is not a loss function as of now, here we are trying to apply a softmax function. So let me softmax function. So h2 is a basically softmax function, that is e raised to a divided by e sum of all the e raised to a, all the outputs of the neurons we are getting exponentially, right? So there's something called as sum, there's some chain of functions are there, that is sum minus 1 and squeeze minus 1. So let's see what is mean by. So let's take an example for that. So let me run the above. So let's take an example of a random tensor called 2 cross 4. Okay, so this is the final output layer that I'm trying to imitate here. So if I print this, so if 2 cross 4, that is 2 rows and 4 columns. So this is what I'm getting from A. Okay, now if I try to apply exponential on all these values, I'm getting this tensor where e raised to 0.49, I'm getting 1.6426, kind of like that. Now once I am able to done this, what I'm doing, I'm applying sum of that. So when I'm doing sum minus 1, so for what I'm doing, I'm going to calculate the sum of each row. So for that, since I have two rows, I am getting two values, so I am getting that as 1 cross 2. So the value of row 1 is something of 6.031, and the value of row 2 is 7.3285, the sum of that. Okay, so that I am able to do that using sum minus 1 function. So sum minus 1 dot shape will give me the size of 2. in this case, 2 columns. Now what unsqueeze is doing is, now unsqueeze what it's trying to do, that we don't want the value or our value in torch of this size, that is 2. We want it to into a proper tensor flow in the particular tensor, that is 2 cross 1. So for that we are using unsqueeze function, where we are going to transpose this function, and what, instead of 1 cross 2 we are going to make it as 2 cross 1. So that's why the torch size is 2 cross 1. So what we are doing is, here also the h2, what we are doing as the output, we are getting it as n comma 4 as output, because this is the output that we want, right? For each n input I am getting 4 outputs, that is what we want. So that's why we apply this all this function. Okay, if you're not if you is going overhead, let's keep it as of now, because we're going to see much more abstraction on top of it. Okay, now once we are able to do that, so this we are going to define a loss function. This loss function is basically, here is cross entropy. Okay, so this is a cross entropy. Okay, and this is a example of cross entropy here. Example for the cross entropy. Okay, so we are taking 2 tensors here, that is 2 y hat has 2 this thing, that is 2 cross 4, 2 rows 4 columns. Okay, so our tensor is and y, we are creating another tensor of 2 cross 0. This is y hat is this, and we want output of 2 cross 0 here. So what we will do, we will try to apply cross entropy here, which is where we are trying to see, based on the value of the rows value, we are applying log on that, that is on the value of 0, in this case 0.3, and at the position of 0, in this case 0.8. So if you remember the cross entropy, we are applying the argmax function, where we are trying to find the maximum value of that, and based on that we are trying to calculate the log on top of that. So once we are able to do that, we are getting the value of 2.5. The same function that we have written here in cross entropy, we are able to do that with the help of torch function. Okay, so we have defined the loss function same as above, and then we are defining the accuracy function also, because it's a classification problem that we are doing. Okay, so let's make a major main our feed forward network. So what is happening, let's see it here. So we have creating a seed, so that for reproducibility. So now earlier we have seen that the kind of network we are dealing with, so we have an input layer with 2 neurons, 2 input x1 and x2, hidden layer has 2 neurons, and output layer has 4 neurons, right? The same thing, so if we have 4 neurons, 2 neurons, so obviously the weight layer here will be 2 cross 2, and for the hidden layer, and the for the weights of the output layer will be 2 cross 4. Okay, so the same thing we have written here. So here we are doing weights equal to random for 2 cross 2 weights. We are assigning the random initialization of weights, and we are doing math square 2. So this is called as Xavier initialization. It I think it has already been taught in this in the theory part. If not, maybe in the next session I will do. But right now, so in the theory, it has been said that there's a different ways to initialize a particular weights and bias, and everything has pros and cons. But most popular is Xavier initialization. That's what we are doing here. Okay, and we are telling that, so weight will be a kind of tensor, so we are telling that it requires a gradient function, because we need gradient of that weights. Similarly, we are assigning the tensors for bias as well, because we have 2 neurons for that. Similarly, for the output layer, we are defining again we are weights for the we are doing the Xavier initialization, and we are saying that it requires a gradient. So for that also we need to compute gradient for weights 2 and for bias 2 as well. Okay, now once we are done it, we are doing the learning rate, and we are doing epochs with respect to it, assigning the values of learning rate and epochs. And what we are doing is we're changing the x train and y train into float and long value for better computation as of now, and we're bookkeeping the loss accuracy and the loss and accuracy with respect to it. Now what we are doing for each epoch that we are trying to run, we are calling the function called model, we are computing the loss function, and then we are calling the loss dot backward, where it is going to automatically perform the find a gradient function of that, and it's going to calculate the loss and accuracy with respect to it. And once it calculates the gradient function from loss dot backward, it is going to update the weights bias of all the parameters that we have seen in the network. Okay, so once it has been done, if we run this function here, let me run this, and we are going to plot the value. Okay, it's taking a little time. Okay, so it is we have trained this value, so where the loss we are doing performing loss and the bias with respect to the epoch, the number of epochs we are trying to print it out. Okay, sorry, loss and the accuracy, the blue is accuracy here and the red line is loss. So we are also printing the loss before training and after training with respect to it. Now what else we can reduce here? So here also we written the code is still big, so here's something we can reduce. So to do that, we are using a function called NN function from the torch library. So what it do? So what is actually doing is the NN function will help us to calculate the loss function, in this case cross entropy. So instead of writing the loss function here and calling this loss function, what we will do, the all code is same as it is, the only difference is we are just calling the cross entropy here. So that is the first change that we have done, where we are directly calling a cross entropy function from the nn.functional class, and we are trying to run this. So let's run this also. So now what we are going to do, all this code that we have written here, okay, let me have to run this part also. Now we're trying to reduce this code by adding the by default function from the PyTorch, so that we can make our code small and small. So so from the earlier explanation, right now we are just changed as of now the cross entropy function, that is a loss function as of now. Let's see what else we can try to reduce it. Okay, so this is the value from cross entropy we are getting. Red is loss and the blue is accuracy. So let's see what else we can do to reduce our code more and more. So we are using something called as NN parameters. So what NN parameter is doing is this something called as NN module. So it is inheriting that, and it is calling the super initialize, it is calling that initialize function of the NN module. Once it is do that, so what earlier we are doing is the weights bias of what we have done earlier. So let's see what we have done earlier. So we defining all these values, right, for weights and bias, and we want to have grad function of all that. We're trying to reduce this value. Instead of writing it manually, we try to reduce it here, and we're also updating the values here with the torch not grad, right? So what we'll do using nn dot nn dot parameter, what we're trying to reduce all this thing to automatically be taken care by PyTorch. Okay, so what we have done here is, so we initialize the weights. Okay, and this is a forward pass, that is a1 dot torch. This is the forward pass, that a1 h1 a2 h2, this is we are keeping as it is from earlier code. And the only difference that we are seeing in the fit function, where so here instead of updating all the parameters, what we are doing, we calling the fn dot parameters, and here whatever the parameters grad function that we are getting from the above, the loss function and the accuracy function, we're directly upgrading it here. So this is the another optimization that we have, optimization less line of code that we have done. So this is the one thing. There's another part that we have tried to reduce the code for. Okay, so I want to maybe after going to this, maybe take some more time. I know I'm going very quick with respect to this, but take some time to understand that what are the changes are happening in the fit function and the initialization function, because now we are reducing the size of the code, because we are calling many things using single line, and all the things will be taken care by PyTorch. So that's the advantage that we're getting, but you should understand it, why it is what we are doing, why we are doing it. Okay, now again earlier what we have done, we have initialized that, okay, this much amount of weights do we have, this much amount of bias do we have. So how we can reduce it without telling it much, writing it manually? So what we can call is, we can call NN linear function. NN.Linear function. So what it will do when you pass 2 cross 2, so it will say that it will assign 4 weights. The vector of W will have 4 weights and 2 biases automatically. Similarly, for the from hidden layer to output layer, we are creating we are trying to create a 8 weights with 4 biases. So this is something we are automatically trying to reduce it, and also we can see that in the forward pass, we just need to call self.lane1x, and it will calculate the pre-activation and the pre-activation function of a1 a2 automatically. So we can see that it is reducing a line of code pretty much. And if we try to run this, so values here are changing. So we are not focusing on right now of how the loss and accuracy are happening. We are most focusing on how to reduce this line of codes as of now. Okay, now after this, so what we have done as of now, uh, we have reduced how to initialize the weights and bias. That's the first thing. We have reduced the forward pass, all the equation that we are writing. We are just reducing the all the equations into one single line of code, small line of code. Okay, we also reduce the upgrading the parameters using the using the fn dot parameter, that is using this nn dot parameter function. We are trying to reduce this all upgrading by itself. Okay, so we have done multiple reduction in the code. Now what else we can do is we can define the optimizer also. Okay, so where we just need to tell the which optimizer do we have, and we have to tell that we have to tell this some called fn parameters are there, and it will take care of every single thing automatically. So we are defining the y hat function. So it will call the SDG. SGD is sigmoid gradient descent. This is here also, if you go to the docs, we can find multiple options with respect to it. So we are defining the like simple vanilla gradient descent or NAG or momentum gradient descent. That is something you can you use it using Optim class. Okay, so for each epoch we are trying to calculate the cross entropy. We are creating y hat and with using the help of with the help of SDG optimizer. Then we are applying for cross entropy. We are calculating the loss and accuracy. Now what else we are doing is earlier in the code, let me go a little above. Here also we are here, even though we put all the parameters into a single line of code, we can also reduce it more and more without giving this condition that torch not no grad and the param in the function dot parameters. What we can do is we can directly use Optim function, where we'll just say the loss dot backward, that is to find the gradient. This is to find the grad for W and B, and we just opt up step. For each step we are finding that we are updating the values, updating W and B with the function that we are having, and then we are initializing the W grad and B grad with 0 automatically. So this much we have reduced in the code automatically, and again we are plotting this. So let me run this code as well. So sequentially we are reducing the size of the code by calling multiple functions into picture. And one more step we are going to do, which we can define, which can reduce our model of sigmoid or feedforward network to much smaller. So what we have to do is, earlier we're defining the weights and biases as well in the parameter size, right? What we have to do, using NN module, we have to call NN.Sequential. In that you have to define your network. So here this NN.Linear will tell about the input layer, and the N.Sigmoid will tell about the hidden layer, that we have to apply a sigmoid function with respect to that, and this will tell about the output layer. And you have to apply softmax function on the output layer. This is something you're defining. So sequentially, whatever the neural network that you want, you can define it using NN.Sequential. So once you're able to do that, and you just need to, in the forward pass, you just need to say self.net into X. So this net is the network that you're trying to build. So all this network that you are building is come down to one single variable called self.net, and in forward pass you're just calling this network function. Let's run this, and you're just calling the fit function here. So you can see that how we are reducing the size of initialization and forward code much smaller with respect to this. another small tweak that we're going to do, that now we have defined this part of initialization and forward pass. What needs to do in the epoch function, we'll call the loss function as it is directly, and because from the loss function it will directly go back to calculating this NN.Sequential, the network that you're finding. So it will automatically calculate the weights and the biases, all this. You don't have to write it explicitly on the model. So you just say function loss model X. So model X here will go back to the NN.Sequential where you're trying to do, and then you calculate the grads from using loss or backward. And then you update the grads using opt step, and then you reinitialize the grads value with 0, and then you just have to return this loss.item. So this much small our fit function has become. From hundreds of lines of code, we're just writing 5 to 6 lines of code into this. Okay, and then the last part is here. If you just say that the class name, that is first network v2, this is the first network v2, with initializing this class with init and forward pass, then you're just assigning the loss function called f dot entropy. You're assigning the optimizer, in this case the sigma gradient descent, the learning parameter LR1, the functional parameters of W and B automatically will be taken care, and just you need to call fit.v2, that this function, and all the feed forward network has been compressed down to 4 or 5 lines of code. Okay, and you're getting the output of accuracy whatever you're getting in this case. So in this case, loss value. Okay, so by this time let's revise what we have done. So earlier we used to write big feed forward networks. Now we have seen that step by step we are trying to reduce it by introducing multiple PyTorch functionalities. So earlier we reduce the code by introducing the cross entropy directly instead of calling a new function. Then we try to reduce the assigning the weights and biases by calling the NN.Linear, and using Optim we are trying to calculate all the grads and upgrade the grads and initialize the grad to 0 automatically using NN.Linear and Optim. So once we're able to do that, the half part of our code has been reduced a lot significantly. Then we try to use NN.Sequential, where you can define your own network. You can define your own neural network. You can define your own neural network for that. Okay, so once we able to do that part also, then we went to once you're able to do that, then we went to this fit function, where we're reducing the all fit function to 4-5 lines of code. We just need to call the loss function. From loss function you can call the model function, where you're actually defining the optimizers and all. Okay, now let's run the same code in the GPU. Okay, so let's run the same code on the GPU and let's see how it is going to run. Okay, so this is the last part of the code. So let me run this. So what you have to do is, in the section 2.59, you have to write device. You have to define what device on which you have to run. So earlier I have written CPU. So let's run this, and you have to assign the xtrain and ytrain data to the device, to particular device. So it will automatically load the xtrain y value on that, and then you're going to initialize your function, the class variable, and then you tell that on which device you want to run this function, and you're going to print and here I'm trying to calculate the time taken to learn the particular xtrain and ytrain value. Okay, so let's run on CPU, and the same thing we have done for CUDA as well, and the time taken to learn the value with same loss with the loss of 1.39 is 0.84 seconds, and the same thing here it will take the 0.89 seconds. So it is kind of pretty much same in this case. Let me rerun this again to see that it's taking some time. It has reduced, so GPU will always run fast. Now what we have done here is I just created a same everything is same as earlier, only what we are doing is the number of inputs particular for each input feature have increased with very high value, that is 2 cross 1000 into 4, that is number of weights for each input will be around 1024 into 4, that is that number of features I have. So if I run this on CPU and GPU, let's see how much time will it take. Obviously GPU will run much more faster, as per now we have seen this. So but right now what we have seen in this second part of session is that PyTorch help us to write the whole feed-forward network that we have hard coded it in the earlier session to just to a few lines of code. And I want you to take some time, because it will take a day or two, maybe a week's time, to for you to fully grasp that how it is you're able to write all this stuff into just few lines of code. And unless until you understand this part, you, because when we're going to write CNN and CNN, RNN or LSTMs in the future, we're going to write simple just few lines of code only. We are not going to go back to write big line, big how it is updating the weights, or how it is updating the grad function, calculating grad function. We are not going to do that. We're just going to call the loss.backward function, where it will automatically will find the partial derivative of that, and it will try to it will update the values automatically. Okay. So in today's session, we have seen the basic intro of PyTorch, and we have seen how to play with the tensor, and how adding GPU in our advantage speed up our time. Then in the second part, we have seen that how we have reduced the feed-forward network code into smaller with less line of code by introducing multiple functional like NN.Sequential or NN.Linear or Optim function and all that. Okay. So if you have any question, please let me know. Please take some time to see that code and take some time to play with it, try to understand it, because in one session I can assume that you can't understand it, and it is quite maybe will go over the top for you. So please take some time to understand each and every part of the code. Okay. So yeah, that's at the end of from my side. If you have any question, please let me know. Otherwise we will end the session here. Okay, so I will take it as that we have no questions. Okay, so from next session, we are going to start the proper CNN models and all, which is the main major basic DNN models we're going to start. And now we're going to use PyTorch with respect to it. Okay, so thank you. I'm stopping the session.